In question 1, we've got George who throws a ball at the target 15 times. Each time the probability of hitting the target is 0.48, and the random variable x represents the number of hits in these 15 throws. Now obviously x is a binomially distributed random variable because we've got a fixed number of trials, we've got a constant probability of success. Each trial is a success or failure, so we can easily say that x follows binomial 15, 0.48. So for the probability of x is 3, we simply plug this on the calculator. We get an answer of 0.0197. And in II, the probability of x being greater than or equal to 5, this will be 1 minus the probability of x less than or equal to 4. Remember that we always need to turn this into a less than or equal statement in order to use my ClassWiz calculator. This is 1 minus 0.07987, which gives an answer of 0.9201. We are then told that George throws the ball at the target 250 times, and we need to use a normal approximation to calculate the probability of hitting the target more than 110 times. So the first thing we need to do here is write down the new distribution for x. It is still binomial, however, n is 250, p is 0.48. We've got a large n and the value for p which is close to 0.5, so a normal distribution makes sense here. So we will be approximating x with y that follows normal mu sigma squared, and we know that mu is np, which is 250 times 0.48, and this gives an answer of 120. And sigma squared will be np times 1 minus p, which is 250 times 0.48 times 1 minus 0.48. This gives an answer of 62.4. So we've got the values for the parameter of the normal distribution. We are asked to find the probability that x will be greater than 110. We know that x is a discrete random variable, and we will be approximating this with a continuous random variable, so we need to apply a continuity correction. One way of doing this is writing two probabilistic statements, one with a strict and the other with a relaxed inequality. So if I want to be strictly greater than 110, it's the same as being at least 111. So the continuity correction will give me 110.5, which is the midpoint of 110 and 111. So this will be approximated by the probability of y greater than 110.5, which gives an answer of 0.8854. In question 2, we've got capital L centimeters being the length of a metal rod, following a normal distribution with a mean of 8 and a standard deviation of x centimeters. We know that the probability of being less than 7.902 centimeters in length is 2.5%, and we need to show that x is 0.05. So I will start by stating that L follows a normal distribution with a mean of 8 and a variance of x squared. We have been given that the probability of L being less than 7.902 is equal to 0.025, and because one of the parameters, the standard deviation, is unknown, I will have to use standardization. So from L we go to Z, and we've got the probability of Z less than 7.902 minus 8 over x is 0.025. Remember, we are deducting the mean and we're dividing by the standard deviation to go from a normal distribution to the standard normal distribution. And now I'm using the calculator with the inverse normal mode in order to find the corresponding value from the standard normal distribution. Now 7.902 minus 8 is minus 0.098 over x is equal to minus 1.9599 dot dot dot. So negative 0.098 is equal to minus 1.9599 dot 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 x. So negative 0.098 over negative 1.9599 dot 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 is x. This leads to x being 0.050009 dot dot dot, and therefore we conclude that x is 0.05 to 2 decimal places as required. In B, we are asked to calculate the proportion of metal rods that are between 7.94 and 8.09 centimeters. So we have established that L follows a normal distribution. The mean was 8. The standard deviation is 0.05 dot 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 squared. So the probability we are between 7.94 and 8.09 is simply found on the calculator. In the normal CD mode, it's 0.848993 dot dot dot, which to 4 decimal places will be 0.8490. We are then told that the cost of producing a metal rod is 20 pence. Anything that has a length which is less than 7.94 is sold for scrap for 5 pence. Between 7.904 and 8.09 is sold for 50p, and anything that's more than 8.09 in length is shortened at an extra cost of 10 pence and then sold for 50p. We need to calculate the expected profit per 500 of these metal rods, giving our answer to the nearest pound. So let's start by considering the probabilities that are involved here. So we certainly want the probability of L being less than 7.94. So on the calculator, we plug in the values into the normal CD mode. We get 0.11507. The probability of being between 7.94 and 8.09 is what we have just found to be 0.848993 dot dot dot. And the probability of L greater than 8.09 turns out to be 0.03593. Can always check that these three numbers are indeed adding up to 1 because they cover all possibilities. And then based on these probabilities, we can proceed in finding the expected profit. So to find the expected profit, I will start by calculating the probability of 0.11507 times 5, which is the amount of money I'm getting from those metal rods that are sold for scrap. Then we've got 0.848993 times 50. These are the good rods that are sold for 50 pence. And then plus 0.03593 times 40. Now why 40? Because we are selling these long metal rods for 50p, but they have an additional cost of 10p. So I'm essentially selling them for 40p. And then of course, I need to deduct the cost of producing each rod, which is 20. And then I need to multiply all of this by 500 because I've got to consider 500 metal rods. This gives an answer of 12,231 pence. I was asked to give my answer to the nearest pound, so this is 122 pounds. In part D, we've got that the same manufacturer is now making metal hinges and the probability of having a fault is 0.015. We've got a random sample of 200 of these, and the batch is accepted only if we've got fewer than 6 hinges that are faulty, and the manufacturer is aiming for 95% of the batches to be accepted. We need to explain whether they're likely to achieve this aim. So I will start by saying that X is the number of faulty hinges. Now X follows binomial 200, 0.015. We've got a binomial distribution. Each hinge is either faulty or not. Now the probability of accepting a batch is the probability of X being less than 6. This is the probability of X being less than 5. I will use my calculator to extract this probability. It turns out to be 0.9176, which as a percentage is 91.76%. Remember, the manufacturer was aiming for 95%. We notice that 91.76% is less than 95%, and therefore we conclude that the manufacturer is unlikely to achieve their aim. The question 3 is on the large data set. We've got Diane, who is investigating the daily total rainfall in millimeters for Camborne. We need to write down how a value of R between 0 and 0.05 will be recorded in the large data set. We know that this is a trace of rainfall, so in the large data set it will appear as a TR. And then in B, we need to use the given statistics to calculate the mean of the daily total rainfall and the standard deviation. Now, starting with the mean, I will call this R bar. It's the sum of the rainfalls over the number of days. This is 174.9 divided by 31 days, which gives an answer of 5.64 millimeters. Now for the standard deviation, we've got the formula sigma is the square root of the sum of the squares divided by n minus the mean squared. We usually call this the average of the squares minus the square of the averages and then square root because we're looking for the standard deviation. In our case, it's the square root of 3,523.283 divided by 31 minus the 174.9 over 31 squared. So we plug this on the calculator, we get an answer of 9.05 millimeters. We're then told that Diane believes that the mean daily total rainfall in August is less in the south than in the north of the UK, and the mean daily total rainfall in Lucharts for August 2015 was 1.72 millimeters. We need to state, giving a reason, whether this provides evidence to support their belief. It makes sense to recall the map of the UK together with the position of the different locations where the meteorological data is available. So this is what it looks like. Lucharts is in the north, Camborne is in the south, and we can simply say that since Lucharts is in the north and Camborne is in the south of the UK, and we have found 5.64 millimeters on average in Camborne, and 1.72 was given for Lucharts, then this means that Diane's belief is not supported. Diane believed that the average rainfall was greater in the north than in the south, and it's actually the opposite. In part D, we are told that Diane uses a large dataset to estimate the proportion of days with no rain in Camborne for 1987 and finds this to be 0.27 to 2 decimal places. We need to explain why the distribution binomial 0.27 might not be a reasonable model for the number of days without rain for a 14-day summer event. Well, if we recall the conditions, the assumptions of the binomial distribution, the first one is that we assume that the probability of success is constant and that the trials are independent. So I could actually start by stating that the binomial distribution assumes that days will be independent, and this is unlikely to be the case because we expect consecutive days to experience similar weather conditions. And we can also say an additional point we could raise that the probability of no rain 0.27 is unlikely to be constant, and therefore we conclude that the binomial model is not a reasonable one for the number of days without rain for a 14-day summer event. In question 4, we are told that the dentist knows from past records that 10% of customers will arrive late for their appointment, and this new manager believes that there has been a change in the proportion of customers arriving late. We have collected a random sample of 50 customers, and we need to write down the null hypothesis and the alternative hypothesis corresponding to the manager's belief. So the null hypothesis is always what we know to be the case from past records. So in our case, age naught is that P, the probability of a customer arriving late for their appointment, is 0.10, whereas the manager believes there's been a change. They don't specify whether there's been an increase or a decrease, so we're talking about a two-tailed hypothesis. So the alternative is that P is not equal to 0.10. We're then told that we need to use a 5% level of significance to find the critical region for this two-tailed test. We should state the probability of rejection in each tail, so we expect to see a statement of the probability of rejection for each tail in our answer. So for this part B, I will start by defining my random variable x to be the number of customers who arrive late, and we can see that under age naught, which means that if the null hypothesis is true, the random variable x follows a binomial distribution with n being 50 and p being 0.10. This is because each customer is treated as a trial. They will either be on time or late, and we assume that the probability of being late is constant at 0.10. We are now looking for the two critical values because it's a two-tail test, the left critical value and the right critical value. So we are looking for C1 such that the probability of x less than or equal to C1 is less than 0.025, and C2 such that the probability of x being greater than or equal to C2 is less than 0.025. So these are the values beyond which we say that we have departed from the null hypothesis, and we will be rejecting the null hypothesis in favor of the alternative hypothesis. Now, on my ClassWiz calculator, I'm going to binomial CD mode. Through trial and error, I tried different values for x until I hit a value for the probability which is less than 0.025. So we notice that the probability of x being 0 is equal to 0.00515, and the probability of x less than or equal to 1 is 0.0338, and therefore we will pick the 0 because that's less than 0.025. So C1 is 0. Now for the right critical value, the C2, we need to do some manipulation. First of all, the probability of x being greater than or equal to C2 is 1 minus the probability of x less than or equal to C2 minus 1, and this has to be less than 0.025. So 0.975 should be less than the probability of x less than or equal to C2 minus 1. Again, on my calculator, I plug in different values. I notice that the probability of x being less than or equal to 8 is equal to 0.9421, and the probability of x being less than or equal to 9 turns out to be 0.9755. Remember, we're trying to get something which is greater than 0.975, and therefore we will go for 9. So we conclude that C2 minus 1 is 9, and therefore C2 is 10. This means that the critical region, we need to specify this in set notation, is all x which is 0, or so union here x greater than or equal to 10. What we are still missing though is the statement of the probability of rejecting the null hypothesis. So the rejection probabilities on the left tail is the probability of x being 0, which is 0.00515, and on the right tail it's the probability of x being greater than or equal to 10, which is 1 minus the probability of x less than or equal to 9. This is 1 minus 0.9755, which turns out to be 0.02454. In part C, we are asked to find the actual level of significance of the test based on the critical region we just found. So we know that the actual level of significance is simply the probability of falling in the critical region, which simply means that we either got x to be 0 or x to be greater than or equal to 10. So the probability of x being 0, we said it's 0.00515, and the probability of x being greater than or equal to 10, we just found it from before, it's over here, the 0.02454, so 0.02454, and this gives an answer of 0.02969. And in part D, we are told that the manager observes that 15 out of the 50 customers arrived late for their appointment, and with reference to part B, comment on the manager's belief. Well, first of all, notice that 15 lies in the critical region. Remember, the critical region was 0 or anything greater than or equal to 10. So we have seen a value that lies in the critical region. This means that we have a significant result. We reject the edge node. This means that in context, we have evidence to support the manager's belief, or alternatively, we could say that there's evidence of a change in the proportion of customers that arrive late for their appointment. In question 5, got a company that's employing 1,825 people. These are classified as being professional, skilled, or elementary, and they live in one of two areas, A or B. We need to use the table here with all the information to find the probability that the employee chosen at random is skilled. Well, we've got 275 plus 90 over the total of 1,825. So it's 275 plus 90 over 1825, the probability of picking a skilled employee, and this turns out to be 1 over 5. Now, the probability of living in area B and not being a professional means they are either skilled or elementary, so it's 90 plus 80 over 1825, and this simplifies to 34 over 365. We are then told that some classifications of employees are more likely to work from home. So 65% of professional employees in both area A and area B work from home. I will start with this piece of information. 65 over 100 times the total number of professional employees. This was 1,120, adding up the professionals in area A and area B, and this gives an answer of 728. Now, looking at the Venn diagram here, the event F is that the employee is professional, the event H is that they work from home, the event R is that they are from area A. So this region here is corresponding to those employees that work from home and are professionals. So we know that a total of 720 employees are professional and work from home. So the number here should simply be 728 minus 247, and this works out to be 481. We are then told that 40% of skilled employees in both area A and area B work from home. So now 40 over 100 times the total number of skilled employees, which is 365, and this turns out to be 146, and 5% of elementary employees in both areas work from home. So now I'm gonna do 5 over 100 times 340, which is the total number of elementary employees. This gives an answer of 17. So this means that if I add these three numbers up, I will be finding the total number of employees that work from home. So 728 plus 146 plus 17, this gives an answer of 891, which means that this region here should be adding up to 891. So to find the number that should be going here, I simply need to do 891, which is the total number of employees working from home, minus all the numbers that appear here. So minus 123 plus 481 plus 247, and this turns out to be 40. Now we know that event F is the event that an employee is a professional, and we know that we've got a total of 1,120 professionals, which means that the number here missing can be found by doing 1,120 minus all of these numbers here. So this here will be 1,120 minus the 247, the 481, and the 133. This turns out to be 259. So this is 259 going here, and there's only one number missing, the number outside. So bearing in mind that we had a total of 1,825 employees, if I deduct everything from 1,825, I will be finding the missing number here. So what I need to do is 1,825 minus the 40, the 123, the 412, the 247, the 481, the 259, and the 133, and this gives an answer of 130. So this completes the Venn diagram. In part D, we need to find the probability of R dash intersection F, which means we are in F but outside of R. So if we are in F and outside of R, we could only be here. So the 247 plus the 133. So in part D, the probability required would be 247 plus 133 over the grand total of 1825, and this simplifies to 76 over 365. In E, we need to find the probability of H union R dash. So H union R is all of this, so either H or R or both. And the dash means the complement, which means outside, and outside of this shaded region is simply the 133 and the 130. So for part E, I will simply be doing 133 plus 130 over 1825, and this gives 263 over 1825. Finally, for F, we need to find the probability of F given H. This is conditional probability now. So we know for sure that we are in H. So I will start by shading H. So we know for sure we are in H. And we are wondering on what's the probability we are also in F. So if we are also in F, it means we are here or here. So I will simply be doing 247 plus 481 over the shaded part here, which is the 40 plus 123 plus 481 plus 247. So the numerator will be 247 plus 481 over the probability of being in H. So 40 plus 123 plus 247 plus 481, and this gives an answer of 728 over 891. In question 6, Anna is investigating the relationship between exercise and resting heart rate. Now she took a random sample of 19 people recording their resting heart rate and the number of minutes. She plotted the result on the scatter plot shown here. We need to interpret the nature of the relationship between H and M. H is the resting heart rate, M is the number of minutes spent exercising. You can see that as I go to the right, so as the number of minutes spent exercising increases, the resting heart rate goes down. So what I need to do is give an explanation in context. The greater the number of minutes spent exercising, the less the resting heartbeat rate. So Anna now codes the data using this formula here and finds the product moment correlation coefficient between X and Y to be negative 0.897. We need to test whether there is significant evidence of a negative correlation. We need to state the hypothesis clearly, use a 5% level of significance, and state the critical value used. So let me start by stating my null and alternative hypothesis. So my null is that rho is 0. Rho is the population product moment correlation coefficient. That's the letter I need to use. If I use any other letter, I will be penalized. My alternative is that rho is negative because I've been explicitly asked to check for a negative correlation. My alpha level, my significance level has been set at 0.05. We know we've got a sample of size 19, and we have observed the sample product moment correlation coefficient value to be negative 0.897. So I now need to refer to my table of critical values for correlation coefficients from the formula booklet. So there it is. We are at the 5% level of significance. So I'm looking in this column, and we've got a sample size of 19. So the critical value is the value here, the 0.3887. We're looking for a negative correlation, so the critical value is negative. So critical value is minus 0.3887 0.887, and this is what we will be using to assess on whether we've got enough evidence to reject the null hypothesis. Now, to reach a conclusion, I usually like to draw a bell-shaped curve here centered at 0. These are the possible values for the product moment correlation coefficient. It goes from -1 to 1. I will start by marking my critical value is at -0.3887. So this is the critical region here. If I fall in this critical region, I will be rejecting the null hypothesis. I have seen -0.897. So obviously we can say that what we have seen is less than the critical value. It's in the critical region. So this is significant. We reject H0, which means that there is evidence of a negative correlation between X and Y. Finally, in part C, we are told that we have the line of best fit for Y on X, and we need to use this to find the model for H on M in the form of H is AM to the K, where A and K are constants to be found. Well, I will start by quoting the model here. H is AM to the K. I will take logs of both sides, so log H base 10 is log of AM to the K base 10. Now this can be written as log H is equal to log of A base 10 plus log of M to the K base 10. So the logarithm of a product is the sum of the logarithms, and I can proceed in saying that log of H base 10 is log of A base 10 plus K log M base 10 using the power law of logarithms. Now, the line of best fit was of the form Y is -0.05x plus 1.92, and it's worth recalling that X is log of M base 10 and Y is log of H base 10. This means that I can rewrite this equation here as log H base 10 in the place of Y is equal to -0.05 log M base 10 plus 1.92, and then I can simply compare with what I have here. So we see that the -0.05 should be matching the K here. So K is -0.05, and the 1.92 should be the log A base 10. So log of A base 10 is 1.92, which means that A is 10 to the 1.92, and this turns out to be 83.17. All I'm missing is for me to write down the full equation. So we have that H is 83.17, M to the -0.05.